Thank you so much for coming this afternoon in this session. The topic is perception deception. We'll be discussing physical adversarial attack, challenges and tactics for DNN-based object detection. So first of all, let me take this opportunity to introduce our lab a little bit. So our lab is called X Lab, which is in terms of the security lab within the Baidu organization. It is led by our chief security scientist, Dr. Tao Wei, who has been taking the leading efforts, not only making sure all the Baidu services and the infrastructures are safe and secure, but also more importantly, creating innovations for the next generation trustworthy, privacy-preserving computing frameworks. And my name is Zhen Yuzhong and prefer to be called Edward. I'm leading the effort in the AI security research, and this topic actually falls into that category. And my interests falls into two different directions. First is adversarial machine learning, those kind of things. Basically, we are exploring the safety and security metrics to the robustness of the deep learning models, as well as exploring the defensive mechanisms to the adversarial attack against the deep learning models. And secondly, we also care about model privacy. So suppose your model is deployed in the cloud service, want to make sure all the computation in the cloud service are trustworthy. So your model output will be correct. Also, I would like to introduce my colleague, Dr. Yunhan Jia, who is also graduated from Michigan Ann Arbor. He has done a tremendous job to carrying out all the experimental results and all the demos you will see throughout the talk. And also, there's another folks, Weilin Xu, who is a PhD candidate from University of Virginia. He also contributes a lot to this project. And also, in addition to the AI security research, we have a bunch of folks dedicated into a system security research. And they've devoted to efforts into creating a technology called MESA-TEE, which stands for the Memory Safe Trustworthy Execution Environment. So this is the first time that the memory safe, trustworthy, and privacy preserving has been introduced as a key feature for the distributed computing framework. And under this framework, we have developed a number of open source projects. First of all is the Rust SGX, which combines Rust programming language and Intel SGX technology to make sure all the sensitive computation will be protected within the SGX enclave without any, also with memory safe guarantees and threat safe guarantees. We also have MESA-Lock, which is user level Linux, which reduces lots of attack surfaces. We also have a MESA-Link, which is a replacement to the well-known open SSL libraries, which eliminates memory vulnerabilities such as the notorious Heartbleed. We also have a MESA-Pi, which enables data scientists to run Python program within the SGX environment without running into memory issues. And last but not least, we have ADV-Box, which is a playground the researchers can play the adversarial machine learning attack algorithm as well as the defensive algorithms using the public available data sets. Last but not least, we are hiring. So feel free to scan the QR code on the top to find out our opening positions. And all these positions are located in Sunnyvale, California. So feel free to talk to me offline or shoot me email in that email address. So let's come back to our talk. First is the disclaimer, sorry. So this talk doesn't target any commercial autonomous driving system, and we don't provide any comments to the vulnerabilities of the perception of existing autonomous systems. And we only focus on state-of-the-art object detection methods, and all the results, experimental results, techniques we show here are just proof of concept. So when we talk about autonomous driving, we really worry about is car safety. It's #1 priority for the automakers because human life matters, right? So back in 2002 to 2010, there were a huge amount of complaints about an unintended acceleration in Toyota vehicles. And in 2010, CBS News actually released a piece of information saying that the Toyota unintended acceleration might have involved in the deaths of 89 people. These might also indicating that's related to the massive recalls over the past the decades. And due to that, NASA actually was called upon an investigation into this matter. And the 30 talented engineers spent 10 months looking into that, and they came back with a 179 pages report. And on the page 17, you can find that they claim this large throttle opening UAs, as described, could not be found. But they also saying that this does not mean it couldn't happen, just because given the time frame they have and the complexity of the problem they have. And a couple of years later, in 2013, actually a second group picked up the problems after what NASA folks had left behind. They actually provided a second opinion on that. They actually found some critical variables that are unprotected under some corruptions, and these corruptions are memory corruptions due to stack overflows or buffer overflows or race conditions. And these bugs cause some tasks to die. And these defects actually are linked to these unintended acceleration problems through the hardware and the software testing. So eventually, as we can see, New York Times has this piece of news saying that Toyota actually agrees a 1.6 billion settlements for a class action after that. So that really means car safety is really important. It costs lots of human resources looking into this problem. It is very complex, and it costs lots of money. And also, early this year, on March the 19th, a Uber self-driving car actually killed a person who was crossing the street in the state of Arizona during the night. This picture was actually taken after the accident when the NTBS folks were doing an investigation on the vehicle which is involved in the accident. And as a result, Uber stopped its self-driving car operations in the state of Arizona. Another very interesting case here is that in May 2018, in the state of Utah, there was a driver who is rear-ended into a firefighter truck, and he claimed that the car was running on autopilot mode. It is really interesting to us because, as we know, autopilot kind of feature, there has to be equipped sensors like radars and cameras to have 360 degrees of visibility, and it also can help them to detect the nearby objects like cars. And how on earth such a big, shining red firefighter truck cannot be seen by these sensors, and also there's no action has been taken based on that. So far, there's no explanation on that. Probably there won't be any, but in this talk, we're trying to demonstrate what we found in terms of the input, the vulnerability in the sensor inputs. So we talked about the perceptions. So in order to get the car to understand its surroundings, it has to be equipped with various types of sensors, such as LiDAR, radar, or cameras. And they work together to identify different driving scenarios. For example, the camera can detect the 2D objects, they can detect traffic lights, they can identify the traffic signs. And the LiDARs, they can detect 3D objects, and the radars can detect objects even in the severe weathers. And these sensors actually enables perception capability within the autonomous driving systems. And coming back to the cost estimates, radar costs like a couple of several thousands of dollars. A LiDAR could cost $10,000 to $100, even more, depending on what kind of resolution you want to have. However, camera only takes several $100s. So that means it is way more expensive for a car to be equipped with LiDARs if you want to do a mass production on that. So that means only a few big players can do that, such as Google, Waymo, Uber, those kind of players. So there's lots of guys, lots of startups tend to use low-cost kind of solution, which is the vision-based object detection. That's why in this talk we are focusing on the vision-based or camera-based object detection. So there are a number of ways to do the camera-based object detections. In this talk, we only focus on end-to-end object detection, which leveraging on the deep neural networks to do that. So as you can see from the image in this slide, basically it is trying to find all the possible places that might have a potential objects. And furthermore, they need to determine whether these places contains an object or not, and also trying to associate this object with a certain class. And these, as you can see, these technologies relate to computer vision and image processing. And here we want to introduce one of the state-of-the-art vision-based object detection method. It's called YOLO. You only look once. So in this slide, I would give just high-level introduction. Basically, given an image, first of all, it will resize it into certain size, which here is 416 by 416 by 3. Then it will downsample it by a factor of 32 until it reaches to a 13 by 13 feature map. And then based on this feature map, it will make predictions on the anchor boxes, which I will talk about in detail later, which is the prior knowledge of the object the YOLO will detect in the image. And also will give detection for the number of classes the training data set has. So basically, if your training data has 10 different classes, it will make 10 different predictions over these 10 classes. So people might ask, why do you choose YOLO as your target? So good news is the YOLO also actually does a great job to do the comparison not only on the accuracy, but also on the performances. So here, for the accuracy, actually the author actually compared the YOLO with a number of different object detection methods. So in this table, you can see they compared the average precision, which is the metric used commonly in the object detection world, the average precision over different IOU, which is intersection over union. And also they measure the average precision over different types of objects. It can be small objects, it could be medium objects, it could be a larger object. So as you can see, if we don't consider real-time as a requirement for the object detection, then the RadioNet, which is the second from the last, has the best accuracy. However, if we just compare the YOLO V3 accuracy with the rest of the methods, you can see the average precision are very comparable. There's not much difference there. Now we come back to look at the performance and see how efficient it is if you want to detect an image, right? So how much is it for the inference time? So YOLO actually takes 51 milliseconds to inference an image. However, the RadioNet, which has the best accuracy performance, would take like 198 milliseconds. So YOLO V3 is 3.8 times faster than the best detection method, RadioNet. And also, when we compare a region-based object detection method, which is faster RCN, YOLO V3 is still like 3 times more faster than the region-based faster RCN. So since we are looking at a autonomous driving kind of scenario, so real-time is really a requirement for us. So that's why we choose a YOLO V3 as our object detection method for the attack. And the animation on the right actually shows the effectiveness of the YOLO v3. We took an image from our parking lot and display it on the monitor and feed it to a YOLO v3 model, which deployed on iPhone X. So you can see all the cars can be correctly identified by YOLO v3. Even you move the iPhone X camera from side to side a little bit, it still can correctly identify these cars. So which means YOLO v3 works perfectly. No, works very well, I would say. Now we pick our target. Let's switch gears to take a look what the current status of the adversarial examples. Probably lots of you already know that adversarial example has very effective to fool the deep learning models to reach to incorrect decisions. So normally in the image world is defined as like given an input image, you need to apply a delta to the input image to craft a new image. So we want to minimize these distances so that human cannot easily identify it. And also at the same time, when you apply the classification function on it, you reach to a different results. And at the same time, after you apply the perturbation to the original image, the newly generated image has to be a valid image as well. And also, the most well-studied distance metric, we call it LP norm. Usually, these are being used to generate these adversarial examples. There are three of those. The first is L infinity, which means intuitively the attacker can make changes to all the pixels in the image. And for each pixel, it's only allowed to be changed by up to a limit. And secondly is the L0. L0 means the attacker can only change the pixel that matters most, which matters most means can have the biggest impact to the incorrect classification results. The L2 is mainly based on Euclidean distance kind of metric. So intuitively, the actor can make changes to many pixels by just a small amount. So next, let me show some examples for these three different kind of LP norms to see how these impact to the DNN results. So first, let's take a look at the L infinity kind of perturbations. One typical algorithm using this kind of perturbation is called FGSM. It is fast gradient sum method proposed by Ian Goodfellow, who is from Google Brain. So the middle image is the perturbation we produced based on this method, and we apply that image to the original image, which is on the left, which results into an image on the right. And once we feed that image to the YOLO v3, as you can tell, the cars actually are misclassified into different objects. Sorry, it could be handbags, it could be motorbikes, so on and so forth. So completely fool the YOLO v3. We also tried the L0 kind of perturbation. One typical algorithm is GSMA, proposed by Nicholas Piepernot. It is called Jacobian-based saliency mapped method. So again, the middle image is the perturbation we applied. We calculated based on these methods. We apply that to the original image on the right, on the left, which results into image on the right. Then we feed that into a YOLO v3. As you can tell, all these cars are mispredicted as backpacks or motorbikes, or even you can tell there's a bird coming out of nowhere. And now let's take a look how the L2 perturbation works. Again, L2 typical algorithm proposed by folks from UC Berkeley, Nicholas Carlini and David Wagner. In the middle is, again, the perturbation results we got by applying this kind of methods. We add that to the original image, which results into a perturbed image on the right. When we feed that into YOLO v3 model, you can see how it works. Again, lots of cars are mispredicted, and also there's a bird coming out of nowhere. Again, so far, what I introduced here, they're still in the digital context, means you can have freedom to make changes to the original image. So the question, or maybe the debate, may come up with that whether this is feasible, whether you can change any pixel value in the image or not, whether you can change the pixel value of the tree or not, whether you can make changes to the pixel value of the sky. These are maybe very valid questions. So in the rest of the talk, we'll try to demonstrate how we achieve this step by step. So first of all, we want to explore the chances of physical attacks against the YOLO v3 in a white box settings. In terms that white box is that we assume we have the knowledge about the original model architecture and the parameters and probably the original training data sets as well. And also, we need to identify the opportunities by completely understanding the YOLO v3 inference mechanisms. So let's get a deep dive into YOLO v3. So as we mentioned earlier, YOLO v3 take the image as an input. It will recess into a certain size, in this case, 416 by 416 by 3. They will pipe this into a series of convolution layer and maximum layers, which involves like a total 147 layers, and there are also like 6 to 1 million parameters associated with that, until it reaches to a 13 by 13 feature map. When they make the predictions, it will make predictions on 3 different scales. There's one 13 by 13, there's a one 26 by 26, there's another one 52 by 52. And as a result, the YOLO v3 actually will make 10,647 predictions on the bounding boxes. So for the training data sets, in my talk, we are using the MS-COCO data sets, which stands for the Common Objects in Context. So in autonomous driving kind of scenarios, there are only like a person, cars, truck, bus, bicycle, motorcycles, and a stop sign and a traffic light associated with these autonomous driving kind of scenarios. But in total, there are like 80 classes in the COCO data sets. As you can tell in the image below, these autonomous driving kind of scenario-related objects, they can be correctly annotated and will be classified correctly. Now let's take a look how the YOLO v3 makes the predictions. Suppose we take the 13 by 13 scale as an example. So each cell in this grid will be responsible to predict the objects. Suppose we are going to predict stop sign here, and the center of the stop sign is in column number 11 and the row number 2. So in this cell, it will make predictions on 3 different anchor boxes. And these anchor boxes are just prior knowledge of the shape and the size of the objects that learn from the training data sets by applying a k-mean clustering algorithm on it. As a result, the model actually learned a tall and a thin objects rather than the wide and short objects. So suppose this stop sign is associated with an anchor box with a shape like 116 by 90. And there is a prediction vector which will do the prediction. This is a fixed length prediction vector. And first I will introduce 4 elements of that, which is responsible for predicting the bounding box. The bounding box, the center point of the bounding box, and secondly, it will predict the size and the shape of the bounding box. So to calculate the center of the center point of the bounding box here, b of x and b of y indicating the coordinates. So basically, it uses a function, sigma function, to apply to the t of x here in the prediction vector as the offset of x from the top left corner of that cell. Similarly, you can get the offset of y by applying the sigma function to get the offset of y from the top left corner of that cell. So that in that way, you got the B of X and B of Y as the center of the bounding box. Okay. Then the next job is you need to know the size of the object. So you need to draw a rectangular around that stop sign. So the way to do that is they use a formula. Basically, they multiply the original anchor box, the width of the anchor box P of W, to the e to the power of T of W in the prediction vector to get the width of the bounding box. And similarly, they got the height of the bounding box by multiplying the P of H to the e to the power of T of H in the prediction vector. That's how they got the size. And now we have the correct bounding box drawn around the stop sign, which is perfect. Next is, just remember the MS COCO datasets have 80 classes. So basically, there will be 80 different elements in this prediction vectors. Each of those actually is a sigma function results, indicating the confidence of the that particular object. And also, the remaining one element is the objectness of that object. Basically, it's the confidence whether this object, this area contains the object or not. So when we multiply these two confidence together, we actually got an overall confidence on whether this object exists there or which class it is. In this case, let's say the stop sign has 99% confidence, and the rest of the class, let's say car, has only like 0.01% confidence, then the YOLO V3 will determine this is a stop sign. Now that we understand how it works, but now we probably have a hunch on how to make the attack by just minimizing two probabilities. One is the objectiveness probability. The other is the targeted class confidence. If we are able to reduce these two probabilities below the threshold, probably we can do the job. We'll explain these step by step in the following slides. So first of all, let me introduce our threat model. We call it physical image patch attack. So suppose we want to fool the detector on a stop sign, and you have your own image patch. Let's say this is a black hat Euro logo. Then you can put it on top of the stop sign, right? And more realistically, if you're driving a car on the road, you can put up a sign on the side of the road and also attach your black hat Euro logo onto it. So to fool the YOLO V3 think that could be a speed limit sign or something else. Another interesting case is that you actually can put your image patch onto the ground and make some fake objects out of nowhere. Last but not least, this is an interesting example we found that lots of yellow cabs actually put up some pad on the back of the car to display some ads. And this could give us lots of opportunity to achieve our physical attack. So here, I will introduce our physical attack approach and objectives. So the approach we take is called input patch construction. So here is how we do that. Suppose you have your own image you want to use to initialize your image patch. Let's say this is Black Hat Euro kind of logo. However, since you capture that with your devices, for example, a camera, and the size of the image, the patch in your camera might be different from the original image. You have to do some resize on it. And also, if you use the patch is seen from different angles or from different distance, the shape might be different. You have to do some perspective transformation on that. At the end, once everything is satisfied, you can put your patch onto the image, right? So the good thing is all the resize operations and perspective transformation operations, they are differentiable, which means you can use gradient descent kind of methods to systematically crafting your own adversary examples out of it. which is great. So in this talk, we're actually targeting two different objectives, attack objectives. One is the object fabrication, making YOLO v3 think there's something out there out of nowhere. The second thing is the object vanishing. So we want to make object disappear in front of the YOLO v3. It's just something very similar to the great magician David Copperfield did to the Statue of the Liberty. Sorry, it moved too fast. So the first objective is the object fabrication. There are two ways to do that. One is a naive fabrication. So if you look at if you look at the image on the right, wow, it's popping too fast. The top image actually shows there's a patch on the ground, but there are multiple objects were detected out of nowhere. The way to do that is we want to push more detections towards a certain object. And the following pseudocodes describe how we did that. So basically, first of all, you need to get the class ID for the target class, which is car here. And secondly, you need to grab all the probabilities that are associated with the detections of the cars. Then you want to get the probability of the objectiveness associated with the detections. And then you need to use your add-on optimizer to maximize these two probabilities. So in that way, you can achieve this type of attack. And secondly is the precise fabrication. Basically, want to bring this to a new level. So basically, want to produce a fake object at specific location. That means we only predict one object out of this image patch. And the way we do that is described in the following pseudocode. And remember, we mentioned the prediction vector before. So basically, since we put the patch there in the image, we already know the location of the patch, so we can pre-calculate this prediction vector. And we can also feed these coordinates of the patch into the model and retrieve all the matched predictions with these coordinates. And we try to minimize the distance between the predictive objects with the prediction vectors. We pre-calculate early. So in that way, when we apply the add-on optimizer, we can actually push the prediction close to the prediction vectors. And eventually, we apply the non-max suppression kind of method to have only one predictions on these specific locations. And secondly, we want to do the object vanishing. Want to make the object disappear in the whole image. For example, in this image, there's a car. We actually attach a patch on the license plate of the car. And you can see that there's no bounding box around the car. Basically, YOLO v3 doesn't think it is a car. And the following pseudocode actually describes how we did it. Actually, it's the opposite way as I described earlier for the naive fabrication. Basically, it grabs the class ID for the target class, which is car, and also grab all the probabilities associated with the car and also the object confidence associated with these predictions, and using a add-on optimizer to minimize these two probabilities. Once the optimization converges, then you can see the bounding box disappears. Now we introduce our systematics methods, how to craft our adverse examples. But these are not enough because there are still challenges to achieve the success of physical attacks. For example, as we mentioned earlier, you're not able to make any changes freely onto the original image source. You don't have the ability to do that. This is a controlled perturbation area. Secondly, if you see the object from a various distance and angles, the object appearances changes. right? And also, different light conditions also will change appearances of the objects. There's also another interesting fact that's called color distortion. For example, in this image, we show a digital color palette, and we printed it out using a printer. We used a Adversarial printer to print it out. As you can see, there is slightly difference in the bluish area comparing to the original digital color palette. And furthermore, we use a iPhone X to capture the image from a distance, and it looks like this, which it has a significant color distortion comparing to the original digital color palette. Last but not least, human might make some errors because you want to, when you generate the perturbation image patch, a human needs to put that to the original physical target. And he could put that maybe just centimeters off the original position, or maybe millimeters off the original positions. It might hurt the attack effectiveness. So here are the list of tactics we use to these challenges. So basically, for the controlled perturbation area, we use image patch-based attack. For the color distortion, we apply the color management with the non-printability loss. We'll discuss that in detail in the later slides. For the inaccurate patch, we use random transformation during the optimization iterations. For the various distance and angles, we actually combine the random transformation with the total variation regulation instead of the expectation over transformation, which is proposed by researchers in MIT. Also, for the various light conditions, this is still in a work in progress. Actually, in this talk, we're taking a workaround kind of solution. We just put the car in the garage to get a stable environment. So let's talk some individual tactics in details. For the color management with non-printability loss, actually this is a method proposed by Mahmoud Sharif from CMU. They had a paper published on CCS 2016. They actually defined an NPS score, which is that they actually define a set of printable RGB triplets. The NPS score is the distance between the given pixel to its nearest pixel in that triplet set. And for the perturbated delta, the NPS score for the perturbed area is actually the aggregation for all the NPS score of the pixels in that areas. So as you can see, the lower the NPS score, the higher probability the color can be reproduced. Also in this slide, we show some results when we applied NPS or how the effects look like. So on the left, this is a patch or perturbation we got without applying the NPS. And the middle one is actually we print that image out and capture that with iPhone. As you can see, when we compare these two, there's significant color distortion there. The white is no longer white, and the pink area kind of turning into a brownish area. In order to solve that, we actually use the NPS kind of solution, which results into an image on the right, which is more smooth, and it can be reproduced by different various of devices, such as printers and iPhones. The second thing is how to deal with incorrect patch. So basically, we use random transformation during optimization iterations to solve that. So suppose you want to apply a patch to the stop sign. However, you might be a little bit off there. It's not perfectly positioned. So the way we do that, we took steps of number of iterations. Within each iterations, we actually we know the location of the patch. And that means we know the coordinates of 4 vertices of this patch in the image. So we can randomly stretch these 4 vertices a little bit. Then we do the optimizing through iterations. Then in the next round of iterations, we stretch out these 4 vertices a little bit again to make into another shape. we run through the iterations again. So on and so forth until we reach to a robust perturbation kind of adversarial examples that can fit for this kind of human errors. To deal with the various distance and the angles, those type of challenges, we actually combines technology we mentioned earlier, which is random transformation and total variance regulations. This is actually a different approach from the expectation over transformation, which requires they do draw a transformation from a distribution. However, we didn't do that. We just simulate that by creating a transformation using the RT plus TV. The rightmost animation actually shows the effects, though that the stop sign is seen from different distance and probably different angles. And you can see most of the time there's no bounding box around this stop sign. That means UV3 doesn't think this is a stop sign. And also, when you take a closer look at the patch we apply on the top of the stop sign, this is also look like a stop, right? So, which means we initialize this patch with a stop sign as well. Actually, the way to achieve this kind of effects is by doing this through a series of transformations. We pick 3 of those occasions to just illustrate the ideas. We show that in the left side. The leftmost one is actually the case that when the stop sign is seen in the relatively far distance. And the second one is when the stop sign moving closer. And the third one is that the stop sign more close to the camera. And also we zoom in the image patch on the top left corner, so to show the difference. So as you can see that in each different occasions, the size of the patch is different, and also probably the location of the patch is also different. So we actually generate the random transformation to for each occasions. When it's far away, when the stop sign is far away, you can see the perturbed patch area. Actually, you have to do more to this area in order to achieve your success. In a way, saying that you will not be able to recognize this is originally initialized as a stop sign. But as you move the stop sign closer, you can see the patch that you only need to modify a little bit, so you still can recognize the patch was initialized as a stop sign. So after this series of transformations and optimizations, we actually result into a very robust adversarial examples that can achieve this type of attack when the object is seen from a various distance and angles. Now we have discussed individual tactics. It's time to put everything together. We call it an iterative optimization. So basically, MPS, random transformation, total variation, they are just part of the loss function in the optimization kind of stage, along with the attack objective we described earlier. So each iteration will run this optimization using Adam optimizer. We run it iteration after iterations until the attack effectiveness has been reached. And you can see the effectiveness we can see from the right animations. You can see the stop sign there starting with a confidence 1.0. And we also zoom in the perturbation on top of it and put it on the upper left corner. And you can see the confidence gradually decrease. At the same time, the patch changes over different iterations. So when the stop sign decrease below 0.3, that's where the point the UV3 won't think there's object there. So there won't be any bounding box there. So hopefully you guys got some ideas about it. Now let's come to our demo. In this demo, I will show basically there are 2 demos here. The goal first is to make the car disappear in front of the UV3. the setup is like this. So basically, we put a camera at a fixed distance and a fixed angle to the cars. And also, we put up a monitor on the back of the car and display some image in the full screen. As you can see here, initially, we displayed the Black Hat Euro logo in the full screen mode on the monitor, and you can see the Euro V3 can perfectly detect that as a vehicle. When we run the demo, and after a while, we switch that image to a perturbed Black Hat Euro logo. As you can see, the bounding box disappears. And later, we switch back to a cat. You can see the bounding box reappear, right? And then we switch back to a perturbed one, then the bounding box disappears again. So in that case, we claim that we successfully achieved the physical attack. Now we want to bring this attack to the next level, which is we want to show whether this attack can still sustain when the car is seen at various angles and various distance. Now we have the same setup, but you can see the monitor already show a perturbed image in the monitor at full screen. And there's no bounding box around the cars at the moment. Now we kick off the demo. As you can see, when we zoom in the camera, and also we move the camera from left to right a little bit, and most of the time, the Euro V3 won't generate a bounding box around the vehicles. When we switch the image back to a cat, you can see the Euro V3 can successfully detect the car. So we claim that we successfully achieved this attack as well. Hope you guys enjoyed that. Last, let me come back to the conclusion and takeaways for this presentation. So with careful setup, physical attacks are achievable against DNN-based object detection methods in the white box settings. While defense is hard, a good safety and security matrix has to be explored. And also we call out efforts for a robust and adversarial example-resistant model that is required for a safety-critical system like autonomous driving system. Now, that's the end of the talk. Thank you so much, and open for questions. Okay. Yes, go ahead.
Maybe a mathematical question. So why don't you consider the L1 norm?
L1 norm. Okay, that's a very good question. So right now, these are mainly, this is 3 different kinds of LP norms described by a paper from S&P conferences by Nicholas Carlini and David Wagner. They have discussed a lot about these L infinity, L2, L0. So that's why we do that. We can do the L1 too, but that will make lots of difference. Yeah.
And maybe a second question.
Oh, sure.
What happens if you would blur the image a bit? Because at the moment it exploits numerical instabilities inside the neural net. Mm-hmm. And if you, for example, merge every 2 pixels mm-hmm. or every 4 pixels together mm-hmm. and make sure that the predictions are the same, so a car and car, probably then this attack wouldn't work anymore. Would it be an option?
Would you please rephrase your question?
Yes, of course. So because at the moment, so this special image or the patch that you do yes. to attack the neural net mm-hmm. Has a very special shape and a very special texture mm-hmm. and very special pixels in it.
Yeah.
And what happens if you would not only analyze the original image mm-hmm. with the full resolution, but also an image that has only half the resolution?
Oh yeah.
And would the attack still work with the same patch?
Actually, that's a very good question. So basically, that's a resolution kind of thing, right? So the patch you have might not have the same resolution as the your target image. So the way to do that, you can use the resize kind of functionality. In the resize functionality, you actually have a number of options. You can do it in a bilinear way, you can do it in a cubic, whatever, those kind of way. But these are something you can leverage on to make the patch more smooth. So in that way, the attack still works. So based on our experiments, the attack still works. You don't have to have the same kind of resolution to your attack image. Hope that answers your question. Sort of.
Sorry to waste everybody's time, but no. So what would happen if you would not, in this image recognition system, you would not only analyze one image, but also analyze warped versions of the same image and lower resolution images, and then only do the conclusion of an object if they are always the same, the predictions in the same area.
You mean the same predictions, same incorrect predictions, or?
The predictions would have to coincide. And if the resolution, if the full resolution has a different prediction than the half resolution, then you would say, well, I'm not sure, let's better stop the car.
Right. So usually
the attacks, are they persistent?
Okay, it's a good question. So basically, this is how it works. So you are usually assume, so for example, if this is for autonomous driving cars, so autonomous driving usually manufactured with certain type of cameras. They might have the same kind of resolution, or may they may have various different kind of resolution, but they will, once they go through a mass production, so there were different, I would say, a handful this kind of configurations, right? So for each of these, it can be controlled. One way you can do that is to produce different models for different resolutions. And you deploy the model to the cars on which camera, if the camera has the right resolution, you use the corresponding models, right? So that will help with that problem. Okay, cool. Questions? Go ahead.
Hi, so there are defenses that are known to work well against adversarial attacks. The previous question pretty much suggested some pre-processing defenses, right? But what we know works well is adversarial training, right, as per Madri's protocol.
True.
Have you tested your attack against any YOLO3 model that was adversarially trained?
So that's very good questions. Adversarial training is one of the defense mechanisms. However, I mean, there's always corner cases, right? Even it depends on how many adversarial training examples you have, right? You might only cover certain kind of corner cases, but we are always able to find adversarial examples, even it is adversarial training. So basically, the point is that the existing defense mechanism, they have their own drawbacks. And Nicholas Carlini and David Wagner, they actually have a paper in ICML, International Conference in Machine Learning, in 2018. They're actually saying that all the existing defensive mechanisms are not working. Yeah.
So have you actually tested against adversarial training with YOLO3?
Of course, the adversarial training will be helpful to improve the robustness of the model. That definitely. I'm not saying that adversarial training doesn't work. It's just saying that it can improve, but it cannot be like 100% like a safe guarantee, because we are running an autonomous driving system there. We cannot tolerate a single kind of life loss. Those kind, right?
I'm so sorry, we're out of time, but
okay.
Perhaps you'd mind taking some questions in person at the end? Without the microphone.
Okay, yes, we can take that offline. Thank you so much.
Thank you very much.